Hi everyone. We'll just wait for a few minutes till more people join. I first of all need to thank Sustainable Education Foundation for inviting me to do this live session. This is the first time I'm doing a live session, even though I've done offline sessions before. This is the first time I'm doing a live session on a social media platform. Hopefully, it will be interesting for you all as well. Um, Till others join, let me tell you a few things about how this all happened. Like I was because when these guys invited me to do a session, I thought of I said to them that I don't want to do an introductory sessions because I think Haritha, who is already here, has done a really good session before as well as, and there are many introductory level machine learning content on the web. So I was thinking of doing a more like a practitioner's guide or like a practical approach to machine learning because that is what I think mostly lacking in Sri Lanka, as well as most of the people have been asking about how to start in machine learning, what is the best approach, how should I, what should be the GPU I should be buying, things like that. So these are very practical aspects of machine learning, and I haven't seen a lot of content on that, especially in Sri Lanka. So that's why I thought of doing a session or a topic like this, even though I'm not an expert. I should say that I don't think I'm an expert by any means, but I have worked on few things so far. So I thought of sharing what I know, and also, so I started writing down things I know, and I thought it'll be like at least I'll be able to get it short, maybe 15-20 slides, but it went longer than that. Hopefully, you will still find it useful. Um, and yeah, okay, I think let's start because these guys have only given me 1 to 1.5 hours. So I need to cover everything within that time. So I'll start. So this is a practitioner's guide to machine learning. As I just said, I'm CD Athuraliya. I am the co-founder of an AI startup called Conscient AI, as well as I am a research fellow at Learn Asia. Uh, so let me tell you a little bit about myself. I was after graduation, I worked at WSO2. Hope you all know, which is a great place to work. I worked in the machine learner team there. There was a product called WSO2 Machine Learner. So the screenshot you can see here is a screenshot from that product. Mm, I met very interesting people there, and I was lucky enough to work with very very intelligent and smart people at WSO2. And then because it's not a great place to work, only because I was more interested in research, I left WSO2 and then joined a non-profit research organization called Learn Asia. I'm not sure how many of you have heard about Learn Asia, but it's also a very nice place to work. It's a unique place, I would say. I was in the big data team as a big data and deep learning researcher. I was mostly focusing on computer vision problems, especially using deep learning. So, as you can see, some of the things you're seeing here, like the analyzing CCTV video footage, things like that. I did that. I was leading some of the efforts, and I was supervising some of the student projects. And also, I was working on working with various other data sets like mobile network operator data as well as satellite imagery, things like that. And I was also lucky enough to, before that, I think I should mention, with, with a very nice and very intelligent team, we could found Sri Lanka's first machine intelligence meetup in 2015. And we've been doing pretty good. Even though we don't have a lot of machine learning experts in Sri Lanka, we somehow managed to host really good people there. And we have done some experimental stuff as well, like doing research paper discussions. Our last event was a research paper discussion, which turned out really well than we expected, honestly. And so I don't know what is the exact reason, but I was very lucky enough to uh, be at some of the conferences held at places like OpenAI and Google, where I met most of, like, majority of these amazing machine learning experts in the world. For an example, as you can see here, this is me with Ian Goodfellow. If you maybe you haven't heard of him, but just do a Google search about Ian Goodfellow. He's the inventor of generative adversarial networks. So I was lucky enough to meet people like Ian, Andrew Karpathy, Chris Cola, Sammy Bengio, and so on. Like, there were many. So the good thing is, these conferences, majority of the attendees were from places like Google Brain, Google DeepMind, Facebook AI Research, and so on. So the conversations, the sessions, the things they were talking were very interesting and very refreshing. So I was lucky enough to be at that conference twice. And also, uh, relatively recently, me with few of my colleagues founded this AI startup called Conscient AI. That's a little bit different story. If I'm to tell the whole story, it would take a little bit of time. So I would just mention that if you are interested, you can also do a Google search and see what we are trying to do, and hopefully we'll also be able to share more information about what we are trying to do. Okay, so that's all about myself. So what is this session all about? This is for anyone who's interested in AI, machine learning, deep learning, data science, analytics, and so on. anyone who's interested in that particular area. But I need to mention that this is not an introduction to machine learning, because as I said, there are so many introductions to machine learning, and you can find them online. There are courses on YouTube, there are tutorials, and many. By an introduction, what I mean is an introduction means things like you define AI, you define machine learning, you define deep learning, and you differentiate between supervised learning and unsupervised learning, and so on. So I won't be doing any of that. Rather, this is, as I said, as the title says, this is a practitioner's approach to machine learning. So I thought of sharing some practical tips and tricks from my little experience compared to other experts out there. Hopefully it will be useful for you all. So, but if you know nothing about machine learning, you should probably do some reading, like before trying to understand everything I'm going to say. But hopefully this video will be available after the live session, so you can come back after doing your little bit of reading. So my assumption about you as a viewer is that you are either involved or interested in machine learning, and you have at least some idea about what is machine learning, what is AI, and how things are positioned like that. So I'm going to skip the basics. Like, I won't be defining what is AI and what is machine learning. You can basically find that from anywhere by Googling. So one of the most common questions I've been asked is how to start in machine learning. And there are variants, but that is the basic question I've been asked most of the time. So, which is a very valid question, I think, because there's a lot of content and there are a lot of things happening. So you might be kind of lost in all this information and all the content around this field. So I think that is a very valid question. So what I'm going to tell you is based on my experience, as I said, as well as what I've seen and read. This is not all my, like, everything is not my first-hand experience. I'll be telling things from what I've seen and also from mostly what I've read. And I would always encourage, as a beginner, as even as an intermediate practitioner in machine learning, I would always encourage a practical approach against reading a lot of theory and trying to understand a lot of theory. But there are exceptions, like if you are a postgraduate student, for example, MPhil or PhD student, who's conducting very focused theoretical research, then it might be the case that you are specifically looking into that particular narrowed area. But I don't think any of you in this audience would be from that category. For general purpose, like data scientists, machine learning engineers, or like wannabe machine learning engineers, I always recommend the practical approach against the theoretical approach. So this is gonna be I'm trying to present this as more like a story. I honestly didn't have time to put nice pictures here and there. I hope you won't get bored. Like, basically the pictures would be really nice. Like there are places like PhD comics to get really fancy, nice stuff. But I didn't have time for that, so it will be a lot of text. But I'll try to explain. So first thing you need to understand is why do you need to learn machine learning, or why are you selecting this particular area? So that is very important. I think in anything if you are doing anything in life, first you need to ask that question. Like, even if you're marrying some person, you need to ask that question, like, why am I marrying this person? So first set an objective. Also, like this for later, maybe even in machine learning we'll be defining a lot of objective functions and optimizing for those objective functions. So setting the objective is important. So it can be for your university project, or maybe you are thinking to apply that in your work. I don't think that is very common in Sri Lanka, unfortunately, yet. Hopefully it will change soon. And maybe even you might be thinking to publish a research paper. That is a one category. I'll call it as group one. And you may be also from, like, you're just interested, or also you're thinking that everybody's an ML expert these days, so why maybe I also should think about it. So something like that. Anything can be a reason. So but it's much better if your objective is from the former group rather than the latter. The reason is, so the former group is you actually have a reason to do something, like more like a quantifiable objective, like you have an undergraduate project to complete, or you have some application at your work, or you are thinking of publishing a paper, something like that, rather than just interested. So the reason is you can then quantify that objective, and there's motivation to do what you're doing. And also you can always measure the progress. For an example, if you're doing an undergraduate research project, you have to make some progress and you need to keep learning. And also there are some progress reports and progress reviews, and at the end of the project you have to submit a thesis, and you need to maybe build a working system. So you always need to reach these goals or milestones. So we can measure the progress, and also there's motivation. So even if you are in the latter group, where like you are just interested, you are just curious about this new field, so my suggestion is to try to make it more concrete, try to make it more like tangible, so that you can. It is again in the first group. Some examples are like you can start following an online course with deadlines. Try to find an industry project. So I won't be repeating what is on the slide, but you can get the idea. So try to work on something that is interesting to you, where you can also apply some machine learning. And also if you can think about it, if you have a really good problem to solve, think about publishing a paper. Select a conference which is close enough and also feasible. Like if you are a beginner, this might not be the best option, but think about it. So this is how you should make just your curiosity more concrete. So you have a solid goal to achieve. So then you must be thinking, I think that is the most common question, as I said, how to start. So if you are an absolute beginner, as I said, just read a little bit. Like if you have no idea, you don't even know what is AI is, or like machine learning is, you just read a little bit, at least do simple few Google searches and try to understand the very basics. And I would still recommend to follow at least one online course. There are many. By a course I mean with video tutorials preferably, because the way these lecturers or the tutors explain in their video tutorials is important to understand some of the concepts rather than just reading. So it's better if you can at least sorry, I couldn't put an overview here, so I'll just quickly go through the slides. So it is like I'll be talking about I hope that would be a good approach, because I couldn't put an overview here. So it will be what to work, and some notes about peers and mentors, and background research, how important is data, and what is the language, and what are the algorithms, and what is a pipeline, and evaluation metrics, some tips on neural networks and deep learning, libraries, hardware and infrastructure, how to keep up with everything, general stuff, and that's it. So that's a very crude way of doing an overview, but because I forgot to do that. So I think that would work. So I'll come back to where I was. Yeah. So I think it's a good idea to follow at least one video course. So there are many. My first choice is Andrew's machine learning course. It's on YouTube. If you don't need to follow if you don't need to complete the assignments, I would again recommend doing the assignments if you are an absolute beginner. And also, a small tip: when you're watching video tutorials, increase the speed till you can't follow. Stop increasing the speed when you cannot follow. Till that, try to increase the speed 1.25x, 1.5x, and so on. So it'll save a little bit of your time. I put some of these good tutorials and the courses here, like the Fast AI. It's on YouTube as well as it's as a separate website. Hugo, he's a Google scientist. There's a course. So if you search these names on YouTube or Google, you'll get there. CS 231N, which is a very popular course on computer vision, created by Fei Li and Andrew Karpathy. It is more like a benchmark course in computer vision. Deep Learning TV is also a YouTube channel, which is very good, not to get a thorough understanding, but to understand the basic. It's a very good, because very short videos explaining one single concept. For an example, what is classification, things like that. So if you search these terms, these phrases on Google or YouTube, you'll be there. And things you would need to start is these are the things ideally you would need, but not mandatory. I'll come to that. Some coding experience would be good, and also some basic understanding about algorithms, like the computer science algorithms. And linear algebra, don't be afraid if you're not from a math background or anything. It's just a fancy mathematical field, but what you mostly need is matrix operations. Matrix, again, don't be afraid. It's not the film. It's again from math, but yeah, you'll understand. And these things are not that hard, trust me. As you start learning it'll come, but it'll take some time. I'll come to that later. And also statistics, mostly probability. These are also like the linear algebra and statistics might you might be a little afraid by seeing these things, but don't panic. These things are easy, as well as as I said, you don't need to know everything. And also there are more nice to have, like more math, of course, optimization, testing, and debugging. I think that the coding experience, as I said, like the general software engineering principles, especially testing your code, debugging, things like that are very important. But don't worry if you don't know any of above. You can learn anything online. So, and again, I think I'll be explaining that again as well. You don't need to learn everything at once, and don't ever try to learn everything at once and then apply. Just learn a little bit and then try to apply. I think that is the best way to learn. Don't try to remember all the theory and definitions and everything, and then hope at some point in your life you will be able to apply that theory. That won't happen. Just try to learn something and then apply it. That would work. So how to start again? So it continues. Don't be notation phobic. I don't think this is a term or anything. I invented it, hopefully. So by notation phobic, what I mean is like big equations. I really wanted to put something like that, but I didn't have time again, sorry. So don't be notation phobic. Be familiar. Like most of the time, like when you see, especially in machine learning, when you see a big equation, like all these Greek letters and all that, but it's most of the time it's just summation, that sigma, and some matrix operations and real integrals. Integrals are most of the time not used. It's mostly summation and matrix operations. And in neural networks, there'll be differentiation, but it is very simple. Uh, if you don't understand some notation, because I myself is little bit, I had this notation phobia to some extent, but now I think I don't have that. Uh, so if you don't understand some notation, try a numeric example. That's the best way. Sometimes it won't be possible if it's a huge equation, but think like that. So all these equations convert into numbers at the end of the day. How it is processed in the processor or in your computer is everything becomes numerical. So that's how these things are computed. So don't be afraid that these things are forever letters like X, Y, and Z. These things will be converted into numbers at some point. So numbers are more friendly, right? So don't be afraid. If you can try an example with numbers. And also there are really good visual explanations on the web. For an example, I've given few here. These are like really good sources. For an example, like the Kola's blog, which has really pretty visualizations. Now it is not very active because he is writing on the next one now, Distill Pub. He's working at Google. There's all all these things are by Google, because Google is actually doing a really good job in machine learning, like even in the knowledge dissemination side. So the neural network playground is again a tool by Google. You will be understand how, like you'll be able to understand how a neural network works and what are the roles of each of these terms, like weights and connections and neurons and so on. Teachable machine is also an experiment by Google. If you Google these terms, you will find these things. And as I said, don't ever try to learn everything and then apply. It won't be possible. So try to apply what you just learned, and most importantly, never stop learning. So if you just learn something and then apply it, and if you think that's it, then definitely you will end there. But keep on learning and learning and applying, learning and applying. Do that iteratively. So, so what should you work on? As I said earlier, try to try to find something that actually matters to you. From university, from work, from wherever possible. Maybe not from any of these places, but you have a problem that you are really interested in, and it can be a problem from another domain which you are interested in. If you are, for an example, interested in medical imaging or something, maybe even art. There are very interesting problems in that domain which can be solved, or which machine learning can be applied to solve that problem. So try to pick a problem like that. But the most important thing is make sure that that problem is interesting enough for you to solve. Don't pick something that you don't really like to do. I mean, for anything that won't work, you need some motivation, and you should be feeling satisfied by solving that problem. And again, don't reinvent the wheel unless you really need to understand something thoroughly. So let me explain that. So I think the first part is clear enough. So don't try to reinvent the wheel. A lot of work has been done already, so maybe more than you think. Maybe the most interesting problem you had in your mind has been already solved. So, but don't think that that's the end of your world. And also, the second part is, unless you need to understand something thoroughly, sometimes we try to implement things by ourselves, even though it has been implemented by someone else, just because we need to understand it better. The best example is there are many neural network implementations only using NumPy. NumPy is mathematical, mainly a mathematical library for Python. So people, if you search this on Google, you'll get some of the examples. People try to implement neural networks purely using NumPy just to improve their understanding. So they know what is going on to the lowest possible level without using any high level deep learning or machine learning libraries like TensorFlow or PyTorch. So if you need to do that, if you need to improve your understanding, then you can probably implement things by your own. But unless, never try to reinvent the wheel. There's a lot of work has been done. Try to take it from there, and try to find a simple but niche problem as a start. This is again this is again very important. I don't know how generic this statement is, but this is what I think the best approach. It needs to be simple. Don't try to solve the huge problems like uh, big problems of the world using machine learning. That is not possible at the beginning. You might be able to go there at some point, but at the beginning, don't try to solve big problems, and also try to make it a niche problem. By niche problem, what I mean is uh, don't try, because when you if the problem you have selected is a very general purpose problem. For an example, if you need to classify some images, whether these are cat images or dog images, very popular example, a lot of work has been done there. You don't even have to do anything. The accuracy is really good, and code is there, everything is there. So you might not be able to learn anything out of it. Like, you can just run an online tutorial and that's it, the problem solved. So, but if you pick something like something similar, also simple but different, it's like applying some existing work on a new domain or new application. For an example, classify local currency notes and coins. By that, what I mean is like pick Sri Lankan. So for future use, I'm doing this for mostly Sri Lankan audience. So I'll be when I say local, it's Sri Lankan. Sri Lankan currency notes and coins. So that is not, that is like technically and theoretically it is a feasible problem, and it is simple enough, as well as it is, but most likely it has not been solved. I know a person who solved this problem, but this is I'm just taking this as an example. This has not been solved. Most likely this has not been solved, or it has not been solved to a very good accuracy. So you can, there's definitely a lot of room to improvements. So pick something like that. So, and also it is much better if your problem has some real world application. So there can be like new opportunities coming in once you maybe publish your results. So pick something like that. And selecting a simple and niche problem will give you a really good understanding about end-to-end machine learning pipelines, like from data collection to prediction. It is very important to understand about end-to-end machine learning pipelines. That's one of the reasons you need to select a simple problem. If you select a big problem, even acquiring data and pre-processing and cleaning them would be really tough. And also, you might not require a deep theoretical understanding or resources if you select a simple enough problem. Like for a big problem, as I said, you might need to solve a lot of problems, and you need to understand a lot of things. And also, you might most likely need a lot of resources. By resources, I mean like the hardware resources, infrastructure. So as a beginner, you might not have them. So start simple. That's it. So yeah, start simple as possible. Like for an example, classify two types first. Like if you can classify something like coins versus notes, and keep improving iteratively. For an example, add more classes, but first start that. I'll be explaining more about how to hit your milestones while you're doing this, and solve problems as they come. Don't I've even now I've supervised and I've talked to people who think too much before even starting to solve a problem. That is like a very common problem I have seen. Like they try to think of all the possible paths and all the possible problems that might come up even before starting. That is not possible. Trust me. You cannot think of all the possible paths and all the possible problems that might come up. If you can, you are a genius, like at a different level. You cannot do that. So the best approach is start doing something, and then solve problems as they come. It's really hard to predict what will happen as you keep on doing things. And yeah, that's all about what to work on. There are more, of course. This is more like a guideline, as I said. So, and I hope you can also ask questions at the end of this session. Okay. So, okay. And some notes on peers and mentors. This is mostly be relevant for undergrad students as well as people who are working on their research projects, maybe undergrad or postgrad. What I've seen is that peers and mentors are very important, and it will they will most likely affect a lot about how, like, the effect would be very significant on your work. It can be either positive or negative. Depends on the people who you choose to work. So first I'll talk about peers very quickly. If possible, find a good partner. By partner, I mean a peer in kind of like an academic terms. So as I said, good peers are extremely important and helpful in anything. And you hope you might have heard like the two heads are much better than one. If you again find the right person, and most importantly, they will push each other to do better. I have worked in both modes, and I must say that most of the great, like, I haven't done much, but most of the good things I've done with peers. And as I said, like, they will push each other. And the reason you need to have these peers is, like, one of the most important things is can validate ideas. Because when you are working in isolation, you might come up with you think that is a really good idea and it is the best idea ever, things like that. But only till you ask someone else, what do you think about this? They will see a totally different perspective of that problem and tell you this is not going to work, this is not realistic. So that is what we call as a sanity check or reality check. You most of the time need that check from someone, and it is always good to have some person to tell you that and like discuss ideas, because when you discuss, things improve if you are discussing with the right person. And that's how you validate your new ideas and improve those ideas. And that is one of the most important reasons I think you need to have a peer. And as I said, it's always good to have different perspectives, because each and every person is different and they will see or look at things differently, and different views are important. And what I realized from my experience, especially at Learn Asia, is sometimes it is much more like very refreshing when you have people from different domains. Like, for an example, computer science versus economics. It is really good to work with such people, but unfortunately there aren't many places in Sri Lanka to work like that. But at least try to find someone who will be a good peer. And also, don't think your friends will be good peers. Unfortunately, it's good if they can, but don't take that for granted, because your friends are your friends. They might not have the common interests or objectives in machine learning or data science as you are. So don't think they will be your friend will be a good peer. It's good if they can, and if you both share the common interests and so on. But don't think it'll happen. So so how to find a good peer? There are a few ways, like be a part of an online or offline community. Communities are really important. That's one of the reasons I thought of creating this machine learning meetup and this Facebook group. If you are not a part of that group, definitely join that group. That is reasonably active and going well. So those are the places where you can find people with similar interests and discuss things and maybe reach out to them. And yeah, so once you find someone, reach out to them, ask for help, ask to join your work. Don't be like, all these things have worked for me at least. I'll talk about that a little bit more in the next slide. Even your friends or coworkers can be good peers. Maybe you just don't know that they are also that you've been, like, as friends you've been talking about other things and day-to-day matters, but they're also interested in the same things and they have been working on these things in isolation. So you might just need to talk about these things with him or her, and to discover that he'll be a really good peer. So that also happens, and that has happened to me as well. And I think you don't have to worry about privacy on this one. So my suggestion is share your interest mainly on LinkedIn, Twitter, blog, and other social media, because that is the best possible way, in my experience, to tell others that this is what I'm working and these are my interests. And other people will find you, as well as potentially they will even reach out to you. All these things have worked for me, so that's why I'm telling. And you will get amazing results. So share and keep on sharing things that you really like and the things you've been doing. And it is always better to keep some focus, because it is not like, especially I'm assuming that you need to master this particular area. Let's say if you need to become a machine learning expert, if you are sharing like all the things all the time, like today it's music, tomorrow it's machine learning, next day it's interplanetary communication or transportation or something, that's fine. But then people will think that you are all over the place, and it would be hard for a person to understand what is your actual interest is. So I think it is important to keep some focus, especially on blogs and LinkedIn. That is more like a professional advice. Maybe on like Facebook it's fine, but especially on LinkedIn and blogs, even on Twitter, a person should be able to understand what are your interests and what is your focus by, like, it's good if they can understand at first glance. So again, a fact about myself: none of my existing peers were my friends. This is a true fact. Now, of course, they are friends as well, but I very boldly reached out to people. Even when I was starting this machine learning meetup, I like created a Google form and shared it with, like, publicly shared that. And people who filled that form were not my friends. They were like people who are interested in this. So fortunately or unfortunately, none of my friends were interested in doing this. So that's how I found the people. Even in my startup, that's the same story. So as I said, like, don't think that your existing friends will become your peers. As I said, it's better if they can, but don't think they will be always. But if you cannot find the right person, like, this is more like a life advice. If you cannot find the right person, unfortunately, it's better to work alone, because wrong person wouldn't make anything better. Like, it will most likely be like only make things worse. So work in isolation if you really cannot find peers to work with. Okay, that's all about peers and next mentors. So you might be thinking, I honestly don't know the, the distribution of my audiences at the moment, but uh, you might be thinking why I'm talking about these peers and mentors. These are not machine learning. This is not machine learning, but as I said, this is a practitioner's guide, right? So you are working with machines and algorithms, but as well as you are working with humans, and you are doing things for humans. You are explaining things to humans. You solve human problems. So it's really important to understand these aspects as well. And another reason is, from my experience, from the things I've supervised and I've mentored, these peers and mentor stories very much important, because I have seen projects fail, projects become successful, because of the choices different people have made in selecting these people. So mentors or supervisors, advisors, same thing, extremely important. But again, only if you find the right person. Mentor is not a peer, peer is not a mentor, right? Both roles are unique and very important. I would say I cannot really say which one is more important, because I personally think both these roles are equally important. Um, for an example, a right mentor can change your life. I'm talking about myself. My undergrad supervisor introduced deep learning to me. I need to say thank you, because that's where I was interested in machine learning and stuff. That's why I wanted to be supervised by him. But he's the one who introduced deep learning to me in 2013. So it was actually early enough, and it was really early for deep learning, because deep learning, this hype and boom started in 2012. So 2013 was relatively early. And that's why I say mentor is very important, and mentor must know something better than you, because if that person doesn't know anything better than you, he's not a mentor. So he needs to know something better than you. It can be different. So if you are working on a very focused problem, for an example, let's take that currency and coin example. If you're working on that problem, your mentor might not know your exact domain, like the vision problems and how to classify things. He might not know at that level, but he should be able to guide you on something, like showing the high level directions. What are the topics to look? And let's say if he's not an expert on anything you're working on, at least he or she needs to be able to tell you how to structure your research project, how to write your thesis, how to write a research paper, what are the conferences to look, things like that. So that person needs to know something better than you. Otherwise, if you pick a person as a mentor only if you think he'll be able to positively contribute to your project, otherwise don't select that mentor. I'll come to that in the next slide as well. So unless you have no control over selecting your mentor, some like at most universities, unfortunately we don't have the freedom of selecting our mentor. So you might end up with someone who is totally irrelevant, but in those cases can't help. But if you have some control over selecting your mentor, even at universities you can actually, like if you're really interested, you can talk to that person maybe informally and say that I would like to be supervised by you, these are my interests and so on. You can change things here and there. I have done that. So as I said, don't select mentor just for the sake of having a mentor. Don't do that, because what happens is, there are, like, if you select someone who's not relevant at all, but he'll be there like just hanging around, and saying things which is not helpful, and it can be a huge distraction as well. And if you publish a paper, if you in your thesis, you have to thank that person. I mean, being grateful is great, but to be grateful, that person has to contribute positively. Otherwise, like you just you don't have to mention that person's name or like thank him all the time for doing nothing. So be careful and don't, especially if you are doing something like an independent research, don't pick a lot of mentors just because you need to have some names there. But there's one exception. uh, if you think even having that person's name in your paper or in your thesis is good, then definitely go ahead, because really, like, senior people, they won't even look at your project. That's the reality. So they won't even know your name. I think this happens all the time in I haven't done a PhD, so this is not my experience, but from what I've seen and what I've heard, like, this happens sometimes with at PhDs, as well as like even at undergrad and like some postgrad projects. Sometimes the supervisor don't even know your name and what is the thing you're working on. But sometimes having their name in your research paper is really good, like for your future, of course. Like I'm not taking any local examples. Let's say, like, if you can take Jeffrey Hinton, he's kind of like the inventor of neural network, like godfather of deep learning. So if you can have Jeffrey Hinton as as one of your supervisors, definitely go ahead, even though he doesn't even know that you exist, because having Jeffrey Hinton's name in your projects is definitely good, right? So those are like more like common sense. Uh, um, and if you're working on your own, and don't look for conventional seniority. Again, if you have the freedom to select your mentors, don't look for like just for seniority. Think more about his knowledge and ability to guide you. And again, reach out to people and ask for help. Don't just look around the people around you. You might not be able to find good people around you, but there can be people somewhere, maybe like at another university, maybe even abroad. So I know people who who have reached out to foreign university professors and successfully got them as their supervisors, not for PhDs or anything, like just for independent research work. So that works. Just try it out. And but you have to remember that typically a mentor or a supervisor is a senior person, and their time is valuable and limited. So get the most out of it, but don't waste their time, right? So it is really valuable. So they might be supervising a lot of other students, as well as they might be doing a lot of things. So if you try to ask everything, like simple stuff, like things you can find an answer by just googling, don't ask your mentor, right? That's not the reason there's a mentor. uh, there are problems, you should ask, like you should reach out to mentors and ask for their help, but it's mostly the direction. uh, Point to things that you don't know that they exist and guide you. It's not about like you got an exception in your code and you can go and ask your mentor what is this exception. You can just Google it, right? But the high level direction and the guidance is what you should expect from a good mentor. Don't expect that person to spoon feed or write your code. So good luck finding your good mentor, right? So I think I'm like trying to rush. So next, we are coming to background research. So all these things are like, again, I'm saying the practical guidelines on doing some machine learning projects. So you might be thinking this is again not machine learning. Yes, this is machine learning, and this is kind of applicable to other domains as well. But I'm talking about machine learning. So background research. It is extremely important that you do background research, right? No matter whether you are an absolute beginner or master data scientist, you need to do your background research or literature review in academic terms, right? So I once interviewed someone who invented OCR for English characters. Like, he was explaining that he tried to build a neural net to identify English characters. Like, first he didn't say that it's English. Yeah, we thought it should be at least Sinhala or Tamil, because that is a new problem. But he has been just trying to uh, build a neural network from the scratch to just to identify English characters. He didn't know that there is a already solved problem, and it was solved in 90s. So that's where this is like this is that is where this part is missing. You always need to have a very good idea about the current state of the art. So you need to spend a reasonable amount of time, and don't think it's a waste. Otherwise, you will end up like the guy I just explained. Nobody would. What you are doing would be completely useless because it is already there, and it is much better than what you are doing. So there's no point of doing something like that. Um, so spend a reasonable amount of time to understand what is already out there, and surprisingly sometimes you would even find that the problem you've been thinking has been already solved. So but that's not the end of the world. There's good news, which is in machine learning most of the things are solved up to a certain accuracy, because machine learning as a field is mostly probabilistic. So you don't solve problem like on day zero it doesn't work, and day one it works 100% perfectly. That doesn't happen in machine learning. If you look at anything, any AI application like your Google assistants and self-driving cars, they don't work perfectly. That people have been trying for nearly a decade now, but they're still getting better, like getting better slowly. So there's always room to improvement. So there are three things you can do when you have some idea about what has been already done. So you can either improve state of the art of existing work. For an example, you would be able to. I'll take simple example, a cat and dog classifier. First, you need to understand what is the accuracy at the moment, and let's say it's 90%. So you can try different things, different algorithms, different approaches to improve that to maybe not a lot. You cannot go to 100% in one day, so don't think like that. Maybe to 91%, or like even 90.5%, something like that. That would be significant. So that is improving state of the art. But again, this is not easy for generic tasks, like the things I just explained, because those things are continuously tried. Like especially at places like Google, Facebook, they are all these generic tasks like object recognition, detection, classification. These are tried by, I don't know, maybe hundreds or thousands of people using GPU farms every day. So generic tasks like improving the state of the art of generic task is not easy. But it's not the case for niche problems. If you can remember, I told that, for an example, improving the current accuracy of classifying local currency, Sri Lankan currency, notes and coins. Uh, maybe nothing has been done, or maybe a very little amount of work has been done, but it's easier to improve that. So I think that is the best way to start. And also, if you become successful in either problem, definitely consider publishing your work. So that's one. And also what you can do is do a new application of existing work. Like again, it's more like the currency example. where you know that this problem has been solved elsewhere in a different domain. For US currency, it has been solved and it is 98% accurate. But for Sri Lankan currency, it's not there. It's maybe 60% accurate. So what you do is you apply the same theory and the architecture, maybe even the implementation with changes to local currency. So that is a good and very useful problem to solve. Those are the two things. I think the second one mostly, like these two things are somewhat related. That is what I can recommend to begin in machine learning as a beginner level machine learning problem. And the third one is fundamental research, theoretical contribution. These things are, I don't recommend these things for, like, if you are a beginner. These things are mostly done for postgrad work, like the MSc, MPhil or PhD. Yeah. So that is all about background research. Then we come to data. Data is ultra important in machine learning. So you must be thinking that algorithms or like the approaches or the deep neural network architectures are the most important. But unfortunately, still in real world, most of the time, data is the most important factor. So my suggestion is, and in real world, most of the time, still, most of the real world problems are solved using annotated data. It is mostly supervised learning. Even the self-driving cars are working using annotated data. Like there are even, like, I don't know whether you have heard, like there are Sri Lankan companies that annotate street images for self-driving car companies, even for Tesla and Mobile. Uh, I can talk about these things more, but I don't think I have time. So don't even think of starting your machine learning project without a clear data acquisition plan. So either you need to have your data when you are starting, or you need to have a very clear plan about how to acquire that data. Without your data or data acquisition plan, don't even start that project, because I have seen many projects fail because they start with very fancy projects and very interesting. They look very interesting, but unfortunately they don't have data. This happens most of the time when you need some sort of, like, mostly the government data, especially in Sri Lanka. It's not easy to get. Like, you might be thinking that now this, what is Right to Information Act is there, everything is there, but there's actually a data website, government data website. Hopefully I won't be sued or anything for this. But if you are thinking to get government data, or like even from private sector, it's not easy to get data. And if you are trying to focus or like structure your project around this data source, make sure that you can definitely get that data. So without that, don't even think of starting. And also, as I said, most of the time real world problems need labeled data. Like, I hope you know what I mean. For an example, again, let's say the cats and dogs example. You need, like, if you are building a classifier, you need cat images with labels that these are cats. Like, image itself doesn't say that this is a cat, so you need the cat label somewhere, maybe in the file name or some other with some other reference. So that is what the label is in that particular example. But in different cases, the annotation on or the label can be different. For an example, I'll give you one more. For an example, in self-driving cars, the data most of the time looks like you have exact boundaries around objects, which is called pixel level annotation, which is very more intensive and comprehensive than the previous example. So that is not just a label, that's a pixel level annotation. So which is somewhat hard to produce. But sometimes you need that type of labeling. for annotation. So make sure that you have that as well if you are doing something related to that. Like if you are building a classifier ultimately in your project, you need labels. If you are building something like if you are using something like semantic segmentation, you need pixel level annotation, and make sure you have that. And there are options like you can do by yourself, but think about annotating maybe 1,000 examples, right? It won't be easy. There are people who like all these labeled data set. Most of these things have been done by humans, but doing alone, like you by yourself doing or labeling or annotating all the images or audio clips or whatever the data type you have might not be easy. So think about that. And there are options like Amazon Mechanical Turk, and even like as I said, even there are Sri Lankan companies that would do annotation for you for a price. And if you are really creative, you can create like maybe do some crowdsource game or something. I don't have a lot of time to explain these things, but search for reCAPTCHA. If you already know that, that's fine. reCAPTCHA is the thing you select when saying that I'm not a robot. It is a company which was acquired by Google. So they did something very smart for annotation. So if you're interested, search for that. So if you're creative, you can do things like that. But my recommendation is make sure that you have data, as well as if you need, most of the time you need labeled data. Yeah, so but there are like exceptions, like in reinforcement learning you don't need annotated data. I'm not a reinforcement learning expert. I'll be repeating that. So but what I know is RL don't need a lot of data or like labeled data. I'm talking about like more like a beginner level machine learning project. So as I said, I've seen a lot of projects fail simply because lack of data. You might be thinking, or you might have heard that there are things like synthetic data or data augmentation. These things are two different things. Synthetic data means like you generate artificial data, like you don't have any actual data point, so you generate everything artificially. But it's somewhat hard to defend that. Let's say even in your like a research project, even at your like when you are defending or you're presenting your work, it's not easy to defend that you used. People will be very skeptical to look at your project if you use like 100% synthetic data. But it's not the case for data augmentation, which is you have a little bit of data. Let's say you have 50 examples per each class, but you need to increase that number. So that's where you can use data augmentation. In very simple terms, it means like you apply things like translation and rotation to existing images, or I'm talking about images here because it's easier, and generate more images. For example, one cat image, you rotate a little bit, now you have another example. Somewhat different. Computer will see it as a different example, but it was generated from that original image. So that is in very simply data augmentation. Throughout this slide set, I have I have put these things like the terminology in bold and italic. Like I have applied both bold and italic. So if you're coming back, like if you're looking at the slide set later on, look at those terms. Those are like the terminology in machine learning. So the best case is there's an annotated data set somewhere to download, which is you are very lucky. But also the bad news is it is very less likely to be a niche problem. So if there's a data set to be downloaded, an annotated data set, most of the people might have already tried that, and different things have been tried a lot. So it would be hard to do a really new thing or like to do an improvement. The worst case, yeah, so even in the best case, there are pros and cons. Same with the worst case, you don't have any data, like I mean, you cannot find anything online, or like it is not accessible. So you have to create your own data. But again, the good side or the upside of it is like you can be the first one to do it. So you are in a very unique position, because if you do it and if you can, let's say, achieve at least some reasonable accuracy, that is definitely useful, and you be able to maybe publish it and present it somewhere, and people will find it useful because you are the first to do it. So even in the best case and worst case scenarios, there are pros and cons. And as a side note, I really like this example, even though I don't have time. So Andrew Karpathy, who's director of AI at Tesla now, so he has annotated the ImageNet, and he is considered as the human benchmark on that data set. If you don't know the size of ImageNet is one of the most popular benchmark image data sets in machine learning. So if you don't know the size of the data set, definitely go check. So Andrew Karpathy manually annotated that. I mean, sorry, not annotated. So he actually like selected what is this and that, like okay, I have to explain. So for every example, he tried to classify each and every example. So he wrote a tool to show that okay, every example to him, and he will try to classify what is it. So that's why his evaluation is considered as human benchmark. Now the machine learning models have passed that benchmark. Now machine learning models are doing better than humans on image learning. Okay, so now we come to more into the implementation side. I think I have. So I'm not looking at the comments and stuff. I don't know. As I said, this is the first time I'm doing something like this. So, but okay. Yes, I don't see a lot of things. Okay, yeah. People have said about Siraj. Yeah, that's a really good YouTube channel. One thing I can say about Siraj is good to like if you need a very high level understanding about something, definitely check his videos. But he's not very thorough. If you need to understand something really well, like deeply for deep understanding, Siraj might not be the best option. Yeah, I actually don't know about the other channel. I think the Code Train. Thanks for that. Okay, let's get back to the slides. So the language. This is purely by observation and a little bit of my experience. Deep learning is, as far as I've seen, mostly Python, for better or worse, and data science. These two things are related but different. Is mostly R. There's a language called R. So I think if you are starting, I think it's always good to pick one of these. But I am very much biased towards Python. I'll tell you why. But pick one based on the direction you want to go. So the two directions I'm thinking is machine learning engineer and data scientist. So these two things are very different, even though these things are related, as I said, like even as fields. So machine learning engineer is more like an engineer, of course, but data scientist is a different person with a broad set of skills. Maybe not a lot of deep understanding about machine learning or deep learning or something like that, but he has a lot of knowledge about communication, statistics, and some domain expertise, like not the machine learning, the other domains he's working on. So his knowledge is more broad than a machine learning engineer. So you need to. So for an example, I personally would like to be like, I don't know whether I am already, but I'm taking the machine learning engineer side. That's what I would like to be. Oh, I think I am. So the language choice is also very much like data scientist more towards R, engineer, ML engineer more towards Python. R is the easiest to learn, definitely, I think, but the problem is it won't scale very well. And by scaling, what I mean is like the deploying the models you train in production and like doing processing terabytes of data, do GPU computation, things like that. R won't work. There are plugins and things, but natively R won't support a lot of them. But Python, on the other hand, is obviously the most popular language in machine learning community, and most of these machine learning and deep learning libraries are there for Python with very good Python APIs. So my recommendation, which is very biased, but my personal recommendation is Python with Jupyter Notebook. Jupyter Notebook is something that it's like a very simple IDE, browser-based IDE, where you can easily, like, instead of doing everything in command line, where you can easily write your code and execute things on Jupyter Notebook. So if you Google these things, you will definitely find. Um, Python is still easy to learn compared to other programming languages like I don't know, maybe C++ or Java. And there are libraries to do almost anything you do with R, but not the other way, because on R you don't get a lot of deep learning libraries and machine learning libraries. The machine learning there are, of course, but for deep learning with scaling and GPU support, you don't get all these things in R. But in Python, you have those, as well as you can do pretty much anything you do with R. There are different libraries. So I'm biased towards R. And there are other options like C++. I put these two things together for a reason. So these things are, I don't recommend as a beginner, but you would need them at some point. C++, Coda, if you are very performance savvy, you definitely need to check them out at some point. Scala, which was an interesting language. I thought it'd be boring or something, but it was interesting. Scala is there mainly because what I think is Spark. Spark natively supports a Scala language. If you're doing like large scale machine learning on terabytes of data, you would need to work with Spark machine learning library, and Scala is the easiest to do. But my recommendation is, again, if you're a beginner, you don't start working with terabytes of data. You won't be able to you would need a cluster, so don't start with that unless you are an expert. Java, again, there aren't many libraries, and language wise I don't think it's the easiest to learn, at least compared to Python. So, but there are some interesting libraries like deep learning for J, but still I don't really recommend if you are just a beginner. Now we come to algorithms. Okay, so don't get deceived by the hype. So if you think for some reason that deep learning can solve everything because everybody is talking about deep learning and everything is solved, there's some, like, it is not totally wrong, or like it is not false, because if you take Google, almost all the really good real world applications are there because of deep learning. But still there are things that cannot be solved using deep learning, and the biggest downside in my opinion in deep learning is it still requires a lot of data. People are trying to solve that problem, but in reality still it requires a lot of data, as well as, since you are working with a lot of data, you need a lot of resources, like the hardware resource infrastructure. So try to go from problem to algorithm, not from algorithm to problems. What I mean is, you don't think that I'll be doing something in deep learning. Rather, pick a problem, as I said, that interests you, and then try to solve that problem. If deep learning naturally comes, then yeah, embrace it. But otherwise, don't think that I'll be doing something in deep learning. That I can't recommend that approach. And of course, if you have a limited number of features, like a lot of maybe some sort of like forecasting weather data or something like numeric values and limited number of features, definitely try basic machine learning algorithms such as linear regression, logistic regression, SVM, especially XGBoost, things like that before going to deep learning. And again, a quick tip, which is until recently, most of the challenges on Kaggle, hope you have heard. Like, if you don't know anything what I'm talking, like Google them from the slides. So on Kaggle, it was mostly the winning solutions for XGBoost, based on XGBoost and ensembles. Ensembles mean like aggregating uh, multiple basic machine learning models to generate a more like an aggregated output. So there are low level machine learning models producing some multiple outputs, and based on that output, maybe based on voting or something, you aggregate that output and get the best output out of those low level outputs, something like that. So, and again, as I said, these terms are important, which are feature engineering and hyperparameter tuning are the two most important things in basic machine learning algorithms. If you are not using deep learning, feature engineering and hyperparameter tuning are very much important. So remember these terms. So I won't be, as I said, I won't have time to explain these things in detail. But if you are coming back, if you are looking at these slides again, definitely search these terms. In simple terms, feature engineering means like pick features. So like in your data set columns, which would give the best output. This is not simple as I just said. So there are ways to do feature engineering and hyperparameter tuning, like grid search. So hyperparameter tuning means, in very simple terms, so in most of the basic machine learning algorithms, there are some parameters you need to specify to get the best output. So it will automatically learn, but before you start training, you have to set things like learning rate and so on. So specifying those parameters, like giving the values to those parameters, it requires a little bit of effort unless you know, or you are a little bit experienced in this field, you might be kind of lost. Most of the time there are defaults, and defaults are good enough, but if the results you are getting are not good enough, you might need to tune these parameters and see what is the output you are getting. So that is what hyperparameter tuning is, and there are ways to do that. So remember these terms and look what they are if you're working with basic machine learning algorithms. But if you're working with images, audio, or video data, you are most likely you will require deep learning. Basically, because it's a lot of data, and you will most likely need more resources as well. Now we are coming to pipeline, also sometimes called as workflows. By pipeline, what I mean is, like, I think it is clear enough. There are multiple stages. You start with some data and you end with some prediction, some output. So there is a pipeline. In between, you will have multiple stages. Even a toy problem or a tutorial you would be running has this pipeline, like from data to inference or the prediction. But you don't have to worry about anything. Like if you're running a toy, like a tutorial on the some tutorial from the web, you can see that they just import the data set using a single command, import iris data something, or mnist. So you don't have to think about how to import data, the pre-processing steps and so on, because these data sets are very much generic and used massively. So they have made these data sets built into their libraries. But in real world, building a solid pipeline takes a significant effort and also time. So mostly for the data. So I have given like two pipelines in a typical machine learning project. First one is we start with raw data. and do some cleaning, pre-processing, and maybe some more steps, and do the training. So we train a model using some machine learning algorithm, using data, and we get a model out of it. Then there's a next prediction or inference pipeline, which is we have a new example which is unlabeled, and we most of the time we apply the same pre-processing steps. Otherwise, the model wouldn't be able to identify it as it is from the same distribution. Apply the same pre-processing steps, and using that previous model, which we got from the previous pipeline, we do the prediction. And again, in real world scenarios, most of the time we apply some rules or we apply some post-processing steps to this prediction and get the final output. So this is what a pipeline is in machine learning. So most of the time, machine learning is only a part of this pipeline. So and building a pipeline end to end is more like an engineering problem rather than just a machine learning problem. So you, as I said, I'll be telling more on that later on. So you need to know things other than machine learning, and you need to think about things other than machine learning, as I said, like the engineering stuff, data cleaning, data processing, data pre-processing, data acquisition, things like that. And building a solid pipeline is not easy as running a tutorial or toy problem. Because, as I said, the real world data, especially if you're creating your own data set, that data set requires a lot of pre-processing and cleaning. In real world, you always get messy data. You would never get very nice, clean, labeled data. So there can be missing data points, some values are missing, some values are out of the distribution, things like that can happen all the time. So there are things you can do to, like, for an example, imputation. Imputation means how to fill missing data. So you need to know about these things, and sometimes doing these pre-processing or post-processing steps would take more time than the actual training or the prediction. So my recommendation is, as same as before, build the simplest pipeline as fast as possible. So don't think too much about like all the pre-processing steps and all the post-processing steps and what is the how to optimize like to the best your final output. Don't worry too much about anything. Do mandatory pre-processing and whatever needed, and use the simplest possible algorithm. Like, don't again think about deep learning or like more complex algorithms. Use like basic linear regression, logistic or something. Like these, like it's the same kind of like the three variants of same concept. So use one of these and see. Like if you only have two classes, you can do logistic, or like multiple classes softmax, or like more like a typical regression problem, linear. Apply one of these and see what you get before thinking too much. So you get your first evaluation metric figure. I'll come to that. Something like, okay, you get 60% accuracy from your baseline. This is called your baseline. What you get from the simplest possible pipeline. So what is an evaluation metric? In simple terms, evaluation metric is, I think it is clear enough. It is used to evaluate how good your machine learning models are. Like there are so many depending on the different tasks. For an example, accuracy, ACC is accuracy, area under the curve, precision, recall, intersection over union, multiple object tracking, accuracy, things like that. So as you can understand, like it is very much dependent on the task. And it is really important to understand which metric will evaluate your model or your solution. It is not about like you cannot evaluate your problem using accuracy everywhere, right? It is very much problem dependent. I'll give you like very quick examples. Like, overall accuracy can be misleading. So for an example, in self-driving car scenario, it is somewhat okay to detect something else as a person. Like it's called a false positive. uh, don't be afraid. Like if you are like if you are learning these things, you will get familiar with. uh, so it's fine to detect something else as a person. Like let's say a tree is detected as a person. It is not it won't kill anything, because it might think it's a person, but it might turn around and do something and still find its way, the self-driving car. But what if it cannot detect a person? There's a person actually, but it cannot detect the person. Then what will happen is, most likely the car will drive and kill the person. It is much more dangerous, and it is much more critical than detecting something else as a person. So false negatives shouldn't happen, but false positives are somewhat okay. So this is just an example. So there are accuracy measures to focus on each of these. Like for an example, if you need to avoid false negative at all costs, there's a accuracy measure for that. So it is important for you to understand what is the best evaluation metric. I think same goes with the classic. It is why I'm saying classic is it is used in Android's course. Classic tumor detection example. Again, it's okay. Like if there's a tumor in some person, uh, not detecting it is very much dangerous, because again, but if detecting that there's a tumor when it is not critical as like not detecting. Hope I'm not confusing you, but so definitely go check these things. So the idea is evaluation metrics are very much important, and those numbers will tell everyone how good your models are. Like for an example, even for you, it's very like if I tell my model is 50% accurate versus 90% accurate, you can easily understand what is better. So that's the purpose of evaluation metrics. But remember, these evaluation metrics are almost all of the time machine learning specific. Don't throw these at people from different domains. Like for an example, let's say you are working with doctors and you are working with in a medical problem, like a problem from the medical domain, and you are saying my ROC, or sorry, AUC is this much. They won't understand, and you shouldn't be expecting them to understand that, because they are not machine learning experts. So uh, again, the example on the slides is like general public is not interested about the IOU value, intersection or union. This is the evaluation metric used to evaluate bounding box, like how good the detection is. But general public is not interested to, like they won't understand what is IO is. They are just interested in knowing how good the driving is. So that's all they need to know, like how safe and how good the driving is. So you need to, like if you are working in a real world problem, and if you're communicating your problem and your results with the others, you need to come up with application level evaluation metric to explain how good your overall solution is. This is not about how good your machine learning model is. This is more about how good your overall solution is. So think about that self-driving car example. We need to know how good the overall driving is. That's a different metric, and you might need to come up with that metric to communicate with everyone. And that coming up with that metric would require more low level metrics, like maybe including IOU. So hope you get the idea. These are two different things, and each one is important. And uh, So you started with a baseline. Hope you can remember what I said. Is that the baseline is the most basic model you got from your the most simplest pipeline, and keep on improving uh, by looking at the evaluation metrics. So you need to both improve the model accuracies, machine learning models, as well as the overall solution. Rarely it can happen, which is like your machine learning model accuracies are going up, but the overall solution is not improving. So you need to think about both of these, because ultimately what matters is the solution, overall solution, not the machine learning part. And monitor always. So uh, I again I wanted to put some like tensor board screenshots and things like that, but I couldn't. Sorry about that. But the idea is there, which is always monitor. Even like if you've been working in machine learning, you should know that even while we are training a model, we look at these metrics, how the accuracy goes up, how the loss goes down, so things like that, even while training. So if the accuracy is not going up in each training step and epochs and so on, we we should stop training and look at what is the problem. There are like many practical problems, like even like the funny ones, like you might have missed something in your code and things like that. And there's also a fact which is like it's not that easy to debug machine learning problems, but like the code, unfortunately, I don't have a lot of time to explain all this, but always monitor what is going on, even at the training as well as while you are deploying your machine learning models. You always monitor how, like, you make a change into your pipeline and see whether there's an improvement or even a decrease in the overall accuracy, and take an action based on that. And there are most of these machine learning libraries support monitoring. Like you can see what is the accuracy and so on while you are training, and you get the final accuracy as well. For an example, on TensorFlow, there's TensorBoard. So that's it about evaluating. And now I'm coming to a little bit more focused stuff on neural networks and deep learning. Again, I'm not going through what is a neuron, what is a neural network, that I'm skipping, because yeah. So before coding, or like before implementing, this is not actually neural network specific, but again, I told this before, but I'm telling again, don't try to invent things, right? So there's, as I said earlier, there's a lot has been done. So definitely check what has been done, what is there already, and yeah, Google the shit out of it before you do something. It is like the formal term is like background research or like literature review. It is there for a purpose. Do that. And if you are conducting more theoretical, so like more theoretical research, look for research papers, and also look for implementations. Like if you are doing a simple work, you might end up with a lot of tutorials and maybe videos and some code examples. But if you are looking for more theoretical or like more advanced stuff, you will get research papers as your results. But even for research papers, most of the time, especially in machine learning, there's an official code release, especially from places like Google and Facebook. They do an official code release by the authors of the paper, mainly on GitHub. So definitely check that. Don't ever try to implement a paper by yourself, unless, again, as I said earlier, you need to really understand that. But uh, I'm not discouraging, but it is not that easy. So always good to check GitHub and check the paper whether they have mentioned about the official implementation and so on. Even if there's no official implementation, there are a lot of implementations out there on GitHub. So first thing you need to do, I've been telling a lot of things, so this is something I need to stress. First, reproduce. right? Don't try to make all changes to your code, or like as I said, build everything from the scratch. F- Once you find something like even distantly related to your work, first reproduce that work. By reproducing, what I mean is first try to run uh, that code in your local machine and get the intended output. Trust me, it is also not that easy. Most of the time, when you clone a repository from GitHub, and there can be like there's a lot of experience like happening all the type of things. But so simply it's not easy. It won't work as expected. So you will have to do like find dependencies, install libraries, and maybe correct some coding errors and so on. So, but first try to reproduce and get the intended output as it is. Then only you should start making changes to that code. Never ever try to make all changes and run, and also don't try to build everything from the scratch. Like you don't have to reinvent the wheel. Uh, and again, especially on neural networks, coming up with your own neural network architecture for a particular task is not easy, right? So I wish if I had more time to explain these things, but typically, for example, I'm not sure whether you have heard like from I'm 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 more biased towards, so I'm mostly experienced on computer vision side of deep learning. So there are many existing deep learning, deep architectures for computer vision problems as well as for other problems, right? Coming up with these architectures is uh, hard. So what? So for an example, there are architectures like AlexNet, ResNet, PGENet, Inception, and so on. So these are like well tested, evaluated, commonly used neural network architectures for different tasks. So coming up with something like this is not easy, because you would need a lot of deep theoretical understanding, as well as you would most likely need a lot of um, hardware resources to do that. So especially recently, things like the Inception and yeah, Google Net, these things, coming up with these things, the way they work is like places like Google, they have Google GPU farms, and they run a lot of experiments daily, weekly, maybe for months, and pick the best performing architecture. So because they have a lot of data as well as they have infrastructure, so it's most of, I can very confidently say it's a waste of your time to think about a very good new neural network architecture unless you have a very good reason. Like if you are looking into a very narrow, specific problem where there's no work has been done, then you might need. But again, I need to warn you that like don't pick something like that as your first project, definitely, even as your second or third project, because it is not easy to like do everything from the scratch. So my suggestion is like try to do something on top of these. Like most of the time, for an example, if you need to classify, let's take that currency example from previous slides. If you need to classify between, let's say, coins and notes of Sri Lankan currency, it's just a classification problem on images. So there are existing neural network architectures to do that. So all you need to do is utilize one of these architectures, and of course, there's the novelties. You are training on your own data. It's a new data set, as well as definitely you will have to do some tuning. Even for deep architectures, you need to figure out how many number of what is the learning rate and how many number of uh, steps to train and so on, you have to do these things. So there's novelty, but you don't have to come up with a new neural network architecture, because mostly these recent neural network architectures are actually really deep. Like if you have seen like the images of neural networks, those only contain like one or two hidden layers, but these things usually have 100 plus deep layers, and these are very more recent ones are connected in more complex ways. So it's not easy to come up with something like that. So my suggestion is at least first try with existing ones. Yeah, so then as I said, but if you have very limited number of features like the columns with numerical values, worth trying like maybe a shallow network, like a network with less than 5 hidden layers should be okay, because it won't take a lot of hardware resources as well. But otherwise, especially on images, video, audio, I don't think you will be able to, like, unless you are doing PhD with a lot of like a GPU cluster or something. I don't think it's a good idea to start building a new neural network architecture. And apply transfer learning whenever possible. So again, this is more like the jargon, the terminology, transfer learning. Transfer learning simply means like reusing weights from a already trained model. It might sound a little complicated. I won't be explaining further because I don't have time. But what I'll see in practically, and even we are most of the time, what we do is transfer learning. So there are existing models which have been trained on large data sets. We won't be able to train those will train those models in our hardware. What we can do is take that models. A model means a lot of parameters, or like a lot of weights, and train on top of that. So assume that the initial model has been trained for to classify between horses and dogs. No, I don't know, houses and shit, trees and houses. But what we are doing is we need to classify between cats and dogs, something like that. This is very basic idea. Definitely check that. But remember, so what I've been telling is like the things to remember and things to look for when you're doing a practical machine learning project. So reusing existing architectures is very important, and also transfer learning is important. And also there are a lot of advantages, like you can easily get to a very good accuracy when you're using transfer learning, and also you don't need a lot of data, you don't need a lot of resources, and so on. So definitely do transfer learning. Okay, now we are into libraries, and oh my, I think now we are getting to the. I think there aren't many slides. Anyway, you can leave if you are getting bored or anything. So, but I would like if you can wait till the last slide, because I'll be telling like more important things there. Anyway, so libraries. I'll be mostly talking about like the Python libraries. As I said, I'm biased towards Python, and machine learning mainly is mostly around Python. So scikit-learn should be okay for most of the basic machine learning algorithms. I'll be like telling things little quickly. For R, there are like literally hundreds of libraries. It can be a little bit confusing sometimes, because for the same functionality there are many libraries. That's how that ecosystem has been built. So it can be a little bit confusing, but definitely for basic machine learning algorithms, R can be even easier than Python. So it's up to you. Unless you like to live dangerously, try to learn something future proof, right? I mean, like there are people who would like to use the latest distro like beta versions and nightly builds and so on. So they are like they are more adventurous people, right? They don't mind like breaking their mobile phone or laptop or like, but unless you are in that category, try to learn something more consistent and future proof, because so it'll be easier for you to keep on improving your skills, as well as it will be basically future proof. Because let's say there's some library to do something today, but it is very at a very beta level, or like it is only it's been developing still, and there are no proper releases or anything. Uh, but it won't be there tomorrow. So if you put a lot of effort into learning that, it is not very future proof. Opposed to a library like very much stable with proper releases and a lot of community, it's easy, and most likely it will be there for at least maybe year or two. So again, this is for like general audience. For more adventurous people, feel free to try out everything, because definitely we need that type of people as well. That's why we are getting all this feedback, and that's how things improve. Everything is starting as a small developer or hobby project, but this is more general purpose advice. So on deep learning, like the scikit-learn, as I said, should be good for any like basic machine learning algorithm. For deep learning and neural networks, Keras, TensorFlow, PyTorch, Caffe, MXZ, and there are many more. But in that order, these things should be okay. And there were like really good, not yeah, there were good deep learning libraries like Keanu, Caffe 1, and Pylearn 2. But these libraries are dead, no more in active development. So I don't recommend selecting one of those. Even you find some good implementation, those won't be, definitely those are not future proof. And again, my possibly biased personal recommendation is Keras TensorFlow if you are a beginner, but it's up to you. And of course, feel free to experiment and pick one. TensorFlow is somewhat criticized for their something called static graphs, but that is also changing. So you might need to Google this one to understand more. But PyTorch, like so, if you take a look at the deep learning libraries, PyTorch and TensorFlow are the most popular at the moment. Both have very good Python APIs. But TensorFlow documentation is really good compared to others, and the community support, because Google is really pushing that. And there's a recently they started a YouTube channel as well, and they have been producing a lot of content on the YouTube channel as well. And PyTorch is mostly recommended for research side than production. TensorFlow is production ready as well, and Caffe 2, which is like a not very related version of Caffe version 1, is the mainly Facebook backed production ready deep learning library. So they have like this research oriented library, which is PyTorch, and the Caffe 2 is the production ready. That's what we will see. So but with TensorFlow we don't have that type of problem. The only problem is they have these sessions and all the static graph scenario going on, but that is also changing. And of course there are many more, like deep learning for J, it's for Java, and there's Chainer, DDeep, and so on, and even more, but you can go check by yourself. But it's, as I said, like if you are a more like stable, if you prefer to be stable and future proof, pick something popular. Like there are some upsides, like as I said, good documentation, community support, tutorials, implementations, Stack Overflow, all these are there for more stable projects, like the more stable library. So if you would definitely hit a lot of problems once you start doing things. So it's easier to pick a more stable one, because when you hit some problem, you will be able to find a solution more easily. So the other side of this is like the reinforcement learning. As I said, I'm not a reinforcement learning expert, but as I know, most of these deep learning libraries have some features for reinforcement learning. But what I can suggest is follow OpenAI and DeepMind on Twitter or like their blogs for more content around RL, because these two are the top companies at the moment who are doing stuff around reinforcement learning. Okay, now we are coming to hardware and infrastructure. I think we only have like 5 more slides. That is also a very common problem. I'll be mostly focusing on the individual or the beginner level side. But as of mid 2018, I'll like just say that at the beginning, like NVIDIA 1080, if you can buy that, 1080 Ti, don't forget the Ti, should be good enough for most problems. But before that, like that is what I can recommend at the moment. This can change, of course, but again, you need to think a lot before. Sorry. This is the first slide on hardware. Uh, don't think about like investing or burning a lot of cash for experimental, like purely for experimenting. Don't burn a lot of cash, and definitely optimize your pipelines before thinking of getting more hardware or like a cloud infrastructure or something, because it can be like it is very likely that you haven't optimized your pipelines, that you see that you need lot of more hardware infrastructure. But if you actually optimize it, you wouldn't need a lot. For an example, sometimes this is also from my experience. For inference or for prediction, you really don't need a lot of hardware resources. For training, you do, but for prediction, you don't. That's why most of the things like work even on your smartwatches, like even in these Apple and other Android based smartwatches, machine learning stuff are running. But it is not training, it is only inference. Inference don't need a lot of hardware resources. So if you are very confident about your training, what you can do is you can, let's say, take like you can do your training on AWS, Amazon, and then use that one only once, and then do the inference later on other whatever the device, Raspberry Pi, smartwatches, on your laptop or something. So think really well before investing in hardware or like the infrastructure. And also there are really good free options like Google Colab, something they launched recently. I think it is. I haven't tried that one because I usually work in my local machine, and we also have a reasonably, no, actually it's a good GPU, but I think it's free, and also you can use GPUs. One of my colleagues is using Google Colab, and also there are like some. This is kind of cheap, but trial periods of some cloud services, and there are some like free options where you have like a limited number of hours per month and so on. But you can use those before like making a real investment in buying or like purchasing something. For an individual, AWS is, as I said, cheap for short term, and you don't need to set up or maintain. You can get an image like the machine with TensorFlow and everything. But if you need a lot of resources continuously, you should probably consider buying a GPU, because with AWS it would cost forever. Like if you're running the machine, it'll keep charging you. And when you're buying a GPU, the most important things are like the video memory and the number of CUDA cores. And now I'm coming to second slide of this. What I can recommend at the moment is NVIDIA 1080 Ti, but it is also not that cheap. This With this you should be really good enough to do most of the things, but there are cheap options as well. And also make sure that you make this this choice like future proof again, because don't try something obsolete, like don't buy something obsolete, because things are changing so fast. um, and but all that is for individual level, or like very economical level. If you are thinking of production at a company or something, AWS can be cheaper even long term, depending on your scale and so on. Because the reason is like, if you are a company and you are doing a lot of machine learning, you if you are maintaining your own hardware, you need a dedicated person, and you need server maintenance and things like that. You need to set up maybe like a new hardware. There are all these costs. So AWS can be AWS or any other cloud service. There's also Google Cloud, can be even cheaper long term if you are thinking about production. But still, what I've seen is like most of the AI startups, not, I mean, like in the US and in other places, maintain their own GPU clusters. Uh, so we, Conscient AI, also have one Titan X. Titan X is a good GPU, but we only have one. Let's see. So that's it about hardware and infrastructure. And this is, in my opinion, a very important slide, and I haven't seen this type of advice, uh, I can say, anywhere else maybe. So how to keep up with all the things happening and all the papers that are getting published, and like there's a lot of progress every day in machine learning and AI, a lot of articles, a lot of research papers, videos. So, so how to keep up with all these, and what is the best way to follow all these things? So my suggestion is, the first place definitely is Twitter. That is the most active social media platform for machine learning. Most of the top research scientists, the evangelists, and like all the interesting people in this field are active on Twitter. Not on Facebook, unfortunately. There are like Jan Lucan, yeah. If you know who he is, he's the inventor of convolutional neural networks. He is active on Facebook because he is the AI director of Facebook. But his posts are synced with Twitter, so these things are also going to Twitter. But there are like few people who are active on Facebook, but mostly it's Twitter. It's around Twitter. Uh, and also there are other options like ML Reddit, Quora, Medium. But the important thing is, especially on Quora and Medium, you need to, as I said at the very beginning, you need to specify your interests when you are signing up, or like when you are signing up, you have to mention that these are the things you are interested in. So when you are getting weekly, daily, or digests, you will be getting relevant content. That's how you. That's an easy way. So the relevant content will be delivered to your inbox, or your whatever the app you are using. And the next point is, most of these social media platforms and other mediums will lead to research papers as well. So what happens is, usually, let's say there's a tweet, some top scientist has tweeted saying that, okay, this is very interesting, something with a link to a paper. Most of the time in machine learning, it's on archive. Yeah, it is pronounced as archive, not archive or something. This one. So at least my approach is, if there's a paper, first of course we look at the title. If the title looks interesting enough or relevant, there are papers, of course, like which is not relevant, or like which is not interesting. First thing is title. Look at the title. If it is interesting enough, at least try to read the abstract, and try to skim through the content, look at the graphics, like not the graphics, figures and the charts and things they have done, and also, if possible, try to read the conclusion. So you started reading because the title looked interesting, right? So if you so then you will be, by reading the abstract and like skimming through the other section, you will be able to understand whether this is actually interesting or whether this is something not relevant to you. If it is interesting, save it for later, so you will be able to revisit the paper and maybe like thoroughly read and try to understand. If it is not, forget that. But even in that forgetting part, what I do is, okay, I'll come to that in the next slide. So also there's a software category called reference management software like Mendeley, where you can manage your research papers. This is mostly for academia. You can manage research papers, you can highlight, you can share between your devices. And also when you're writing a paper or your thesis, you can uh, easily import references from these tools. So use something like that. I use Mendeley. So it's much easier to keep uh, the research papers saved, and we can highlight and it will be synced across devices. And yeah, think about using a tool like that if you're really into this field. And again, back to Twitter. So what I do is, like, there are really interesting threads going on Twitter, because most of these experts are on Twitter, and follow these top people. Like, I have given examples for everyone. All these people are very active on Twitter, like people and the companies. Of course, scientists. Some top scientists are not active on Twitter, but most of them are. So you will be able to, like, the Ian is definitely active. Actually, Ian is time to time sharing Twitter threads where he'll be starting with one tweet and keep on replying to the same tweet, like the best practices on trading, like on like something like best practices of doing something in machine learning, things like that. He shares. So, and there are people like Jack Clark, who's the communications director of OpenAI. He's not into the most technical side. He's not a scientist or anything, but he's also aggregating a lot of content and he's sharing a lot of things. And he also initiates a lot of interesting discussion. And definitely AI startups, like, of course, OpenAI, DeepMind, Clarify. There are so many, but at least follow the top ones, so you'll be getting things. And also there's the research departments or research divisions of these big companies, like the Google research recently renamed their whole research thing as Google AI. I don't know, maybe they are not doing any other research anymore. So now the Google research Twitter page and blog and everything is now Google AI. There's Microsoft Research. There's, like, on pretty much every, even as I remember, eBay Research, things like that. So there are Twitter profiles for each of these research divisions, and typically they share a lot of content around AI and machine learning because it's one of the hottest research fields at the moment. And that's how I keep. That's the way I get most of the content and updates. Even the papers, like, someone would suggest that best way to keep. Like, I know that I've seen that top scientists, they keep on looking at archive itself. Uh, Maybe checking daily. I'm not that intense. I have to admit. What I do is, like, but I think using Twitter is more like a good filter, because if something comes up on Twitter, it means that paper is significant. So if people keep on sharing, Twitter will suggest you that, okay, these people have liked to share, retweeted this, so you also should probably check that one. So it's a more like a natural way of filtering things, because if you are looking at archive, anybody can basically publish a paper on archive, so we cannot filter them, like, unless you read all of them. So I think it's a good way to follow. Even on Facebook, I personally follow some of the pages and profiles, but what I notice is like on Facebook, it's not that active. And also, don't follow everyone you see, because you will end up with too many things. So it's more like 80-20 rule. Like if you follow like right maybe 20 to 50 people, you get like the 90% of the things happening. That's for sure, because most of the things are like same thing is retweeted by most of these top people. So if you follow one of them, you are most likely getting like there's no point of following a lot of similar profiles. So you won't be getting redundant content. But again, this is more like an advice. Don't try to learn everything you see, definitely, and it is almost impossible to be realistic. Just remember. So I was telling something at the end of the previous slide, which is uh, there's something called exploration versus exploitation. Both are important. The meaning is like you focus on something and you are working on a particular project, or like you are working in machine learning in general. So that is more like you are applying different techniques and you are using certain algorithm. That is exploitation. You are using it. But exploration means you are looking for new things, and what is going on is more like you are getting a lot of content from Twitter. So the difference is the import. You might be thinking that you can just focus on one thing and keep on doing that, keep on exploiting, but that won't work because a lot of progress is there. And if you don't know what is happening, and if you don't know about the new things happening, you might get stuck, and you wouldn't know at some point in the work you are doing, you would get stuck at some point, and you wouldn't know to go beyond that. What has happened beyond that point? So to know that, you need exploration. Uh, so that's why I said in the previous slide, when you are, even if you think some paper is not that interesting or not that relevant to what you are working at the moment, try to keep that in mind at some corner. I don't know, that you saw that one. So maybe even after a year, you start working on a new problem, and you suddenly remember, okay, this was I have seen this one in this paper. So you can at least go back to, and you can try to find this that work again. So that is an important piece of advice I need to give, which is keep on both, like doing both exploration and exploitation. And that's it. So this is the last slide. No, yeah, general stuff, right? This is not machine learning specific, but I think this is very important. Like my personal advice is again, try to master at least one thing first to some extent, then focus on another. Like if you, even if you're interested in, like if you think like I'll be a machine learning master and know everything in AI, something like that, that is not very practical. You cannot, like, even the AI as a field is huge, literally huge. I think any field is huge. Like if you take physics, so like you cannot learn everything in physics. So start focusing and master something at least up to some extent. If you are confident that you know at least as reasonable, you have some reasonable amount of knowledge in that particular field. Let's say, okay, basic machine learning algorithms. You know how to solve a simple problem using basic. What is the best approach? What are the preprocessing techniques? What is the best algorithm, and so on. Then move into the next, maybe deep learn. So that is more feasible, in my opinion. That is a more feasible approach than trying to learn everything at once, right? These things are pretty much obvious, but also we have, like I have seen a lot of people trying to do these things. And the second one is more obvious, like use common sense, but I had to put it because I've seen people doing things without common sense. Unfortunately, yeah, use common sense, right? I mean, I don't have time to give examples, but it's simple. Use common sense. I hope it's simple. You don't, yeah. And the other important thing is you don't get machine learning problems in real world. Right? What you get is problems. So you might be able to apply some machine learning to it, or you might not. Like, don't think uh, machine learning as a silver bullet or something. You can apply on everything and solve everything using machine learning. That won't happen. As I said, like to solve a machine like a real world problem, you need even a basic pipeline, and machine learning is one stage of that pipeline. There are more stages or more steps in solving that problem. So don't think machine learning as a silver bullet, or like don't look for machine learning problems. Like if you talk to some person from another domain, he would say that I have this problem, and you would think this is not a machine learning problem, but that's how the real world problems are. Biggest uh, uh, one of the biggest problems we've seen in the newcomers is that they look for machine learning problems. They don't know how to convert a real world problem into or rather break down a real world problem into a more low level tasks and use machine learning in different stages. So that is a skill we don't see. So remember that one. And also, as I said, like machine learning cannot solve everything, at least yet. So, as I said, like again, solving a problem end to end requires a lot of other things as well. And also follow an engineering approach whenever possible. This is more like these advices are mostly like you would make more sense out of these things once you start doing things, especially in real world, like production scenarios and so on. Like you can code like a really crappy code, and you can write really crappy code, and like you can just get something out of it. But it's always good to follow some standards and guidelines, make some like like maintain clean code. Like basically engineering practices are good anywhere, so try to follow that. In especially in machine learning, there's a general problem of not following these guidelines. It's not something we have only here, it's everywhere. So people are trying to push people to follow these general principles, guidelines, styles, and so on, because it makes things better and easy to maintain, easy to understand, and so on. So yeah. And finally, it's not that hard. I've been telling a lot of things. I don't know any of the persons who at the beginning are still following. And if you are there, like, wow, it's not that hard. It's not hard. Anything is not hard. But you need to focus and keep on doing it. You won't be able to be an expert in 1 week. Definitely, that can't. That is not possible. I don't think on anything you cannot become an expert within 1 week, even 1 month or something. You have to keep on doing, try out different things, and but stay focused and keep on doing. That's all. And especially another thing I've seen is like, don't think you are a machine learning expert because you ran some tutorials, right? You are not. Because most of the things I've already discussed. And don't, especially at the interviews, don't tell you are a machine learning expert or you know machine learning just because you ran some tutorials somewhere. Because you will be honest. Say that you have like you are familiar with that. You know the concepts. Say like that, but don't say that you know machine learning, because if they ask more questions, you won't be able to answer sometimes. Yeah, I think that's all. I So Google has recently published a really good guideline on the good best practices. It's a really good one. I also so I'm also still reading it, and yeah, and anytime you can hit me up on any social. I'm Google CD Athuraliya on Twitter, Facebook, Instagram. I don't know, LinkedIn, anywhere. I'm CD Athuraliya. So Google, find me. You can shoot me an email or something. And we are doing meetups. Hopefully, we'll be able to we'll be doing, but the frequency is problem. And there's this Facebook group. Join that group. Yeah, good luck and thanks a lot. And I need to thank again for Sustainable Education Foundation for uh, so that's why I got this opportunity to talk to you all. So thanks a lot for listening. I don't know honestly what's the next step. Uh, I check. I don't see a lot of questions. I don't know whether it's a good thing or a bad thing. It's like I can just end the session. More than two, almost 2.5. I've been told there's one question. I only see this question about the feature selection measures. So there's a comment on comment asking, can you explain little bit about yeah, can you explain a little bit about feature selection measures? That is, there's nothing called feature selection measures. What you do is you select features. So the feature selection, or it is called, as I said, feature engineering is mostly done by. It's more like an art, honestly. What you do is you try. What you do is, as I said, you have a metric like let's say for simplicity, accuracy. What you can do is you you train a model with all the features you have. Of course, that's the best thing. That's the first thing you can do, and you get some accuracy. Let's say you get something like 60%, and then in feature engineering, what you do is you keep on creating new features, or you select. There are different ways. You select subset of features. Again, for selecting a subset of features, there are ways like principal component analysis, which is like the optimizing for the best features that contribute to the model accuracy. So you keep on selecting a subset of features and building models out of it, and then look at the evaluation metric, whether you are the metric is going up or down. And also you can create new features. For an example, a very simple example, you have a, let's say, a distance feature called distance, maybe between some points. You can create a new feature from that feature, distance squared. The reason is you might not see. So we might not. It may not be very intuitive why we are doing this, because the distance and distance squared. But sometimes there are correlations between these new features, and they affect the final model accuracy more positively than the original feature. It was a very basic example. It might not be the squared always, so it might not be simple as that. But the feature engineering means like, so you keep on doing this, and you select the best possible subset of features or the new features you have created. So the important thing is you always need to monitor what is happening as you do this feature engineering with your evaluation metric, whether it is improving or the metric is going down. And the good, so this is mostly, these things are done in basic machine learning algorithms. One of the plus points of deep learning is you don't need to do these things. So that's why, so the deep learning will automatically figure out because there are feature hierarchies, a deep learning will automatically figure out what are the best features, and it will actually, it creates new features for you, like the in the hierarchy. So in the lowest or the first layer, first hidden layer, those are like lowest possible features, lowest level features. And as you keep on going up or towards the final layer side, those are more and more abstract features created by the new deep neural network. So that is the best thing, one of the best things about deep learning. There's another question. That's a very good question actually. So the question is, what is your recommendation? First being a software engineer, then get into ML straight away, or getting into ML? That's a very good question. So we have actually seen that a lot, and it might sound somewhat counterintuitive, but unfortunately, it's not unfortunately. It's, what we have realized is it's always good to have some industry exposure. Like being a software engineer for some time is always good, because especially in machine learning, what you do is like the way you implement things is by coding, like programming. So if you don't have the industry experience or the software engineering, like the engineering background, what happens is you basically write really crappy code. Like you don't know any engineering approaches or best practices. So sometimes you would your code might work, but it is literally, it's really crappy. So it is not reproducible. It is hard to maintain that code. It is not easy to follow. And like as it was in my slide, engineering practices are always good. Like following those guidelines and best practices is always good. So unless you really need to be purely an academic, still my personal thinking is like, still it's good to be at least like for 1 year some industry experience. But if you really hate that, that's fine. So if you really need to be an academic without doing any sort of like implementation or like the coding, then you should be probably okay without being a software engineer. But I mean, like especially in US and other countries, like they really do a lot of implementation as well. So having that engineering background is like in the actual engineering environment industry is always good. Try to have that if possible, if you have time. Try to get that experience. Um, so you have that background before you get into machine learning. I myself was a software engineer before in anything machine learning. Mm, so I think there are no questions. You can, as I said, always um, contact me if there are more questions or like anything. So because it's more than like, yeah, 2.5 hours, I'll end this now. Thanks a lot again for joining and listening. If you are still listening, there are 11 people. Hmm. So okay, thanks a lot, and thanks SCF for the opportunity. Good luck.